Good morning, everyone. This is Mike McGinn, your online instructor for Net I 105 in the Cisco Network Academy. Today we're going to talk about Chapter 9, which is the subnetting of IP networks. In Chapter 8, in regards to IP version 4, we learned about IP addressing and the role of the subnet mask, which is the mechanism by which an IP address is segregated into its network identification portion and its host ID portion. Now, what we talk about in Chapter 9 is actually altering the subnet mask in order to alter the number of host IDs or the number of networks that we have with a specific IP scheme. So the question might come up as to, well, why would we want to do this? You would think that if it would just make it simple if we just pulled back the subnet mask to make the network as large as many hosts as we have. And in small networks, this works pretty well. However, in large networks, it creates some problems. If we used a flat network design, for example, if we had, say, a large network of, a couple thousand computers, and we used a class B network, which would be a 255.255.0.0 subnet mask, that would create a tremendous number of host IDs, more than what we would need for, say, a couple thousand addresses. But the problem comes in is that if you have all these hosts on a single network, what will likely happen is that certain protocols that use broadcast messaging would be a significant amount of overhead on the network. An example would be DHCP. DHCP is the protocol, as you recall, that assigns IP addresses to DHCP client computers. So if you can imagine everybody coming in to the office at 8 a.m. and all of a sudden 2,000 computers come on, and let's say that the DHCP lease time was relatively short, say it was 4 days, that means that 25% of your computers on every given morning would be sending out broadcast messages throughout the network trying to locate a DHCP server. That could have significant negative impact on the performance of the network. So the process of segmenting a network by dividing it into multiple smaller network space is what we refer to as subnetting, or subnetworks, which they are sometimes called, or subnets. Subnets can be organized a lot of different ways. They can be organized geographically, by department or device type. So there is a lot of different ways that you could do it. I want to share my screen right now. This example in 9.1.2.1, what they show here is they show three different networks based on department: a student LAN, a faculty LAN, and an admin LAN. So another reason you might want to segment a network or subnet a network is for security reasons. As you can imagine, the students probably should have very limited, if any, access to the faculty LAN, and probably very little, if any, access to the admin LAN. By virtue of segmenting the networks and putting each of these departments on a different IP network, we create a level of security where it is very difficult, if not impossible, for computers on one subnet, say the student LAN, to have visibility of any computers on the faculty LAN. So what has to happen in order for communications to occur between multiple networks is there needs to be a router or a device that can function as a router, or sometimes referred to as a layer 3 device, that based on policies or access control lists in that router, it will forward traffic appropriately to the IPs that to the hosts in the various LANs that allow access from other LANs. A layer 2 switch can't do this. So if you think that you can segment your network with a layer 2 switch, and you want to be able to, say, share a printer that's on one network with the other subnetworks, that's not going to work. In order for you to be able to do that, you need a layer 3 device somewhere. Either the switch has to be a layer 3 switch, or you have to have a router. And a lot of times companies will use what is called a stub router, which is just a router off the switch that just takes inbound and outbound traffic and makes those decisions on a trunk port to forward traffic from one LAN to the other, or from one subnetwork to the other. So to reinforce what I just said, on 9.1.1.2, they have a little graphic here that shows a couple of subnetworks and a router. And so for subnetwork 1 to be able to communicate with subnetwork 2, it will send traffic out its default gateway that is assigned to that subnet, and will make a determination as to whether that traffic should be forwarded to network 2 or to subnet 2. So the router is key to subnet communications, or a layer 3 device, as I mentioned previously. So allocating your network into separate subnets requires some planning in your network design process. You need to consider how big is your network, what are the number of hosts per each subnet, and how the host addresses will be assigned. So for example, on the third point, how addresses will be assigned, an example would be like printers and servers will be assigned a static IP address, which makes sense. Users will receive IP addresses from DHCP servers using /24 subnets, and routers are assigned the first available host address in the range. Now, that's just one way of doing it. It's really up to you in terms of how you want to do it, but it's important that for planning that you identify it. I also recommend that you be consistent from subnet to subnet in terms of how you're allocating your IP ranges. It just makes it easier to deal with from a support standpoint, and to make changes as far as changes that you would need to make in the event of growth or even contraction of the network. Typically, subnetting occurs on the private IP network. As you recall, there is a block of public IPs in IP4, and there is also a block of private IPs in IP4. And your ISP does subnetting, or ISPs I should say, does subnetting of the IP blocks, the public IP blocks that they allocate. They are given a large network, say a class B or network, and then they basically subnet that class B network. So they're given a 255 or a /16 network, and then what they do is they parse that out to their customers to subnets that can go as far as 255, 255, 255, 252, which would give the customer, say, 4 IP addresses. So the ISP does subnetting all the time. As far as network administration and local network planning is concerned, you're going to be subnetting private IP addresses. So in basic subnetting, what we're doing here is we're taking the normal network portion of an address. So in this case we're showing a /24 network, 255, 255, 255. So the network address is 192.168.1.0. That's our network address. And of course the host portion is going to be 8 bits long, which is what we're showing here. When we subnet, what we do is we borrow a bit from the host portion of the address by adjusting the mask. And so what we now then are able to do is we are able to, in this example, we're being able to take this network and break it into 2 subnets, the 0 and the 1, by just stealing 1 bit. So the new subnet have the same subnet mask, which is 255, 255, 255, and then the binary 1000, which would be a 192 or 128. It'll tell us on the next page. 128, yes, or a /25 network. So by adjusting the mask to /25, we are now able to take the 192.168.1.0/24 network and split it up into 2 networks that are 192.168.1.1, 1.0 and 1. I believe it'd be 1.28. So we now have 2 networks that we can have as totally separate entities within our network. So in practice, this is what we would have. We would have a network, and they just show 1 PC here, and we have a network that is the 192.168.1.0/25 network, have a router in place, and then we have a separate network that is a 192.168.1.128/25 in place. And if it is required that traffic traverse between subnets, then those policies or access control lists are configured in the router. So calculations of the network address, first host address, and last host address, and the broadcast address for the 192.168.1.0/25 network are shown here. Obviously, the network address is .0, and our first host address is 1, our last is 126, and our broadcast address, as in a /24 network, is the last address in that range, which is a .127. And then when we move to the 128, network address is 128, first host address is 129, last host address is 254, and then our broadcast address, of course, is the 255 address. So that's basically what's going on with subnetting. It's not that difficult until you start, you know, messing around with variable subnet masking and things like that, which we're going to get to in a little bit. So there are some calculations that they will take you through, some formulas that can be used to determine numbers of subnets, the number of hosts, and things like that. In practice, I'll tell you, you're never going to use these formulas unless for some weird reason you don't have access to the internet. Subnet calculators or IP calculators are all over the internet. If I ever need to figure this out just to make sure that I don't make a mistake, I usually just go to a calculator, plug in the numbers, and to get my answers. Obviously, since you may want to learn some of these formulas for the final exam, and be able to work them, because Cisco does require you to be able to be proficient with calculating this stuff manually. Um, but in practice, you would probably use a calculator. So basically from 9133 through really till you get to 91315, there's just a barrage of activities and explanations on how to calculate host portion, the number of hosts, um, and those types of things, number of networks, et cetera. And so you're going to need to spend a little bit of time and a Red Bull or a Java Monster or something, or a good cup of coffee to get your mind sharp to be able to concentrate and get yourself proficient with this. It's just a matter of training your brain to get used to working with this world of IP addresses and subnets. So the question you might run into is, okay, well, how many bits do I borrow when I start subnetting? Well, the answer is pretty simple, is that you got to borrow as many bits as the largest network that will accommodate the number of hosts for your largest network. So if, say you've got 100 addresses in one of your networks that you're going to want to keep as its own subnet, you need to make sure that you don't take too many bits such that you can't accommodate the number of hosts in the largest network. And they talk about that here in 9141. Sometimes you just need a certain number of subnets, and that's kind of the focus. You've got, too many, you got a lot of departments, or you got a lot of locations, et cetera, or a lot of WAN connections, and you need to really have a lot of different networks. So they talk about that in 9142 and also in 9143. So 9143 is a pretty good example of what you might run into. So you've got 5 LANs. Each of them have a certain number of host requirements. And so what you need to do is you need to come up with a network address that will support the number of networks you need and can accommodate the maximum number of hosts per network on any given network. So this here at 9143 kind of takes you through that explanation. And again, this kind of shows you from an IP standpoint and from a network standpoint, these are all going to be, you start out with a /22 network and you are borrowing bits to make it a /26 network, and therefore you can accommodate all the different network addresses that you need and still have plenty of space here for the maximum number of hosts that you would need for any network. And they go through the calculations here that they take you through to be able to derive that. And what you end up with is you end up with a network scheme such as this. So after they put you through all that and all the labs and packet tracers and activities that go along with it, yeah, fun. Your probably brains like mush by the time you get to this point, which is when they start talking about variable length subnet masking. Well, as you can probably imagine from your activities previously in this chapter, or if you haven't done the activities previously in this chapter and you're just blitzing through this presentation all at once, you waste a lot of IP addresses when you're using a fixed mask for all your subnets. For example, you may only need, your largest network may need 250 hosts, and your smallest network may only need 2, say for a WAN connection or something like that. So consequently, you're going to waste a lot of addresses on that small network. This is especially true if you have lots of small networks and very few large networks. So to efficiently allocate IP addresses and also for security reasons, there's a good incentive to try to design your network in such a way that you can minimize the amount of wasted IP addresses. Now, with the word of caution, you don't want to design your IP scheme so that, say you got 15 hosts, and you say, okay, well, I'm only going to subnet that network for 16 hosts because 16 is more than 15. Well, that's great until you add a couple more hosts, and now that subnet isn't big enough, and if your subnets are contiguous, that's going to make changes, it's going to impact multiple subnets. So you do want to provide a little bit of room for growth in your subnet design. I usually try to leave 25% to 50% room for growth in every subnet that is created, just to make sure I got my butt covered if there's some unexpected growth within that subnet. So 915 section here starts talking about variable length subnet masking, and 9151, as we talked a little bit previously, discusses how traditional subnetting with a fixed mask just wastes tons of addresses. Variable length subnet masking kind of it deals with that. Here's a traditional example of a traditional subnetting is creating a bunch of networks, all have 30 hosts. But with a variable subnet mask, what you can do is you can take one of those 30 host networks and you can further adjust the mask on those networks to break that up into many smaller host networks to accommodate, say, your WAN connections or something like that. So what variable length subnet masking is, it gives you a technique to do that. 915 basic VLSM shows you, again, an example of a basic subnet. Shows you that you've still got some unused available, and you've got these that are allocated to LANs A, B, C, and D. So here we are taking the 224/27 network, I believe. Yes, the last subnet. And we are adjusting the mask to /27 from /27 to /30. And what falls out of all of that is all these additional networks. So you might use these three networks for various WAN networks, and these are still multiple networks that are unused. So basic VLSM in practice, you got a network topology here that is all /30, and it shows the actual configurations of the routers that would need to be done of the /30s. On that. And then what you can do is then with the WAN connections, you can adjust the masks so that you can reduce the number of wasted IP addresses as they show down here in this next section. So you get some get an activity to learn how to do practicing VLSM. So you'll want to spend some time on that. And then In 9.2, they start talking about planning the address space with the context of VLSM. And one thing that they do talk about, and we talked about this earlier, is being consistent and have a plan in terms of what types of hosts are going to be using what host ad portion of the addresses. So, so for example, in a 1.0/24 network, perhaps your host devices are going to be from 1 to 229. You're going to save the space of the host IDs of .230 to .239 to be specifically for servers, which would be fixed IP. Your 1 to 229 might be your DHCP scope if your host devices are DHCP clients. Printers, again, given another block of IPs within that subnet that you will manually or fixed address, as well as intermediary devices like managed switches, things like that that you want to be able to get to might be yet another range. And then, of course, your gateway or router typically is the last usable IP in the address range. So this is real important that as you start designing networks or you inherit a network, that you take a look at how things are being structured. And if it's a mess, work on gradually getting yourself to a more consistent structure. And you want to be consistent between subnets and how you do this, if at all possible, at least to the point where if you're going to have the first block of IPs in the range of usable IPs be DHCP scoped host devices, you want to be consistent from subnet to subnet and do that across the board where you're supporting PCs and the like on that particular network, as well as with servers, printers, etc. I always like to see the gateway address be the last IP on whatever subnet I'm using. So that's all, you always know what your router interface is if you know the subnet. So you got a lab on designing an IP4 addressing scheme and designing, implementing a VLSM addressing scheme, etc. So you're going to want to go through all of that and get yourself comfortable. I think I've mentioned several times earlier in the chapter that really in terms of what you're going to take with you out of this class, if you decide that you're going to have a career in IT infrastructure, Chapter 8 and Chapter 9 is the stuff that you're going to use a lot if your job is primarily configuring IP devices, Cisco networking devices. So I can't emphasize enough that this is a chapter, and as well as Chapter 8, that you want to spend a time on. That's why I gave you guys a little extra time in the course calendar. I wanted to make sure that no one by virtue of class load, et cetera, blitzed this and didn't comprehend what was in it, because I think this is where the value add in the course is for you long term. Okay, so if that isn't enough, we have IP6. And IP6 is a little easier. Actually, it's a lot easier. You have masks in IP version 6, but there's just so many massive IP addresses out there, and basically what you get assigned from your ISP from an IP version 6 global unique address is you get a 48-bit network. Okay, so that leaves you 16 bits of subnet IDs that you can use. If you use a /64 network as your internal network, for which you have 16 bits, which is just a ginormous number of networks that you can have internally, and it still leaves you 64 bits for your interface ID, which gives you a ginormous number of hosts. So here's an example. Of course, everything is noted in hex, but this is the number of networks that you have just right out of the box, not doing anything special with a /64, and that goes on, just and on and on and on. Okay, So I think you got uh, up to 65,536 subnets with a /64 mask on an IP version 6 address. I bet you thought it was over. Well, there's one more little twist here in IP version 6 that you need to be aware of. Sometimes what a lot of companies do is they do change the subnet mask from a /64 to a higher number of bits to reduce the number of available host interface IDs or host addresses. And this is done by basically changing the mask to say a /68 or a /72 or a /76, etc., depending on how much you want to pare down the number of available host IDs on a particular subnet in IP version 6. Now, subnetting is done on what is called nibble boundaries, in which creates subnets by using an additional hexadecimal value. So nibble boundaries are 4 bits. That's why you'll typically see masks of /68, /72, etc. 4-byte increments, so that it represents basically a change in the hexadecimal value. So you have some assignments that are due on November 13th that relate to Chapter 9. And you want to do these. Also, I highly recommend that you beat yourself up with the activities that are in the chapter. You really need to get this stuff to become almost second nature with you. I know it's hard, but you know it pays off in the long run, because I will tell you that the final is hard. You may have found that, oh, okay, I do the work, I'm going to pretty much score, pretty close to A caliber grades on most of this course just if I put in the time. Well, I can tell you right now, the final is going to be a whole different ballgame. So that's why the final is, I think, worth 25% of your grade. Because if it was worth 75%, we would have a lot of people that would have a tough time passing the class. That's how hard it is. And the reason why it's that hard is that's how hard the Cisco certification exams are. I've taken plenty of them. They stink. The questions are not written real clear in a lot of cases, and they go for the obscurity. It's pretty easy to do about 60% on them, but you got to really kind of cram and really know your stuff to be able to pass these things on our first try. I would say the vast majority of people that take the certification exam probably don't pass it their first time unless they've gone through a course like this and have applied themselves, or they have really spent a couple months with the learning curriculum that's out there and really crammed. A lot of people even purchase test engines such as Test King and things like that for the particular exam, where there's a lot of uh, example test questions that you can go through. Also, I have found in the test engines I've looked at, if you get one that's recent, it's pretty much got most of the test questions that are on the certification exam verbatim. So if you have the resources, I'd for and you want to get your CCNA certification at some point, the Test King thing or the test engines are really a good investment because I think the certification exams now, unless you get a voucher or something, are a couple $100. So it's not cheap. You don't want to have to take it 4 or 5 times. So anyway, that's Chapter 9, which is your Week 10 assignments. So make sure that you're real comfortable with Chapter 8 and Chapter 9. Again, very key to not only doing well on the final in this course, but also to carry you well as you move into your IT infrastructure careers, if that is indeed the direction that you end up going. So anyway, next presentation will be on Chapter 7, which is Layer 4 TCP, and so look for that real soon.